transmitting. And I just gave away something. Yeah, happy. But I need to find out what is the power level that they're uplinking their signal if it's going up to satellite. They're uplinking. What's the power level that they're going up to the satellite, and what's the power level and frequency that they're coming back down from satellite to Earth with, and what are the impending losses that I'm going to have from my point of transmission into Digicel or Lime, or whatever their name is, and how do they condition my signal to transmit my signal if it's going up via satellite to that uplink, downlink, frequency and power level to the point where it is desirous to go. That's one method. Another method it could be people use other method apart from satellite to get from point A to point B. So Jamaica has a fiber optic ring around Jamaica. So I could get into Digicel or Lime using fiber optic. Jamaica also have fiber optic that goes offshore to Miami, to Cayman Island. And you could choose to use the fiber optic facility because it already exists. And then you could agree with the service provider. How do you go through their system using optical medium to get from point A to point B? It could be a mixture. It could mean that I'm going terrestrial microwave system from my location to a Digicel location or a Lime location. Cayman Wireless could decide to take that and convert that terrestrial microwave link to satellite link, uplink my signal, up and downlink my signal. When it reaches New York, from New York to New York service provider station to the location where I want my signal to terminate, they might only have fiber optic links. So it could be fiber optic for the third part of the journey. So I started regular microwave signal, or I could use coaxial, I could use twisted pair, I could use fiber. Get into a Digicel or a Lime, and they could use their best method to get the signal from point A to point B. But whatever they're going to be using in your design, which means that you're going to have to talk to some people at these places now, to find out, because this is a real design we're talking about now. Realish design. But whatever you're doing, you're going to also now think about two budgets. One is a budget, as I said, the actual cost analysis budget to bring the service from point A to point B. And you're going to also have to think about the second thing, which is called a link budget, which is a power consumption budget that takes the signal from point A to point B. And during all of your design, from the initial communication to where you want it to go, you're gonna have to make a determination as to what are the equipment that I would need, why am I using this equipment, the technical specification of the equipment, why you choose a particular value. So let's say that you choose to use your signal at 10 dBs. Why are you using that? Because that has to pen out in terms of link budget to see whether or not it will survive. The signal will survive from your transmitter through your system to your receiver and still has high enough power level at the receiver based on the receiving equipment to actually receive the signal in a manner that is usable. So in a nutshell, that's kind of what you're expected to do. Questions?
Okay. So I understand the information that we are supposed to be producing pertaining to design, to the design section of it. Okay. So we have the information, but in what format should we present the information? That was kind of one of the major issues I was having. So we know that we're supposed to give you have all the information pertaining to like the kind of equipment that we're going to be using, why we use it, as well as the cost analysis and the power budget and so on. But how are we supposed to present it really? That because I don't really have an idea as to how it's supposed to be laid out and things like that. So they have like an exam. So that's why I was kind of asking for like a visual example, because I actually don't know how it's supposed to be like laid out, presented.
Okay. All right. So be that as it may, what I can do is I can provide you with an example. So I can post an example in the group in terms of what are the requirements that we're looking for, if that's what you're asking.
Okay, fair enough. As long as it also shows like how it would it would be laid out in terms of like
well, the layout really and truly is up to you. You're doing a report on a system that you have designed, and you're given a technical report. You're writing a technical report on a system that you're designing, which is why it's a final assessment, another final exam, because you're gonna have to now do a little bit of research as to see how technical reports are written. So you have your detail and what are the requirements for a technical engineering report. Are you following me?
So what's the name of the kind of report that we're doing? So we know what to research exactly.
It's a technical report, a technical engineering report. How do you report technical? How do you report technical matter in terms of an engineering report? Okay.
Travis wanted to say something, sir.
The platform is free. Say it, Mr. Travis.
Yeah, I wanted. Can you hear me?
I'm hearing you.
Can you hear me? Oh, I wanted to know if you have to do like the noise calculations for like the signal over water or like trees, like attenuation, if that's required, or
You're gonna do a thing called link budget. And link budget is gonna tell you what are the requirements.
All right.
Yep. So I think called link budget is what you're gonna be doing. And in doing link budget, you'll see what are the things that are supposed to be a part of.
So when you send that when you send the information in the group, sir, things like the link budget would be stated as well in it.
No.
Because I was researching technical engineering reports, and they don't really go into much detail pertaining to like what it entails. So it's more like you'd have to already know what is supposed to be in it. And so because we've never done one of these before, so that's why I'm asking. So that's why I'm kind of really confused as to like what exactly we need to put in there.
As I said, I'll give you an example about you doing, as I said, technical report. I'm actually looking for one to post up the example right now. But yeah, the expectation is that you're gonna include almost everything that I mentioned just now. There any other question? I'm actually, as I say, what you mentioned. Otherwise, we continue, and I will post an example in the chat.
Sir, that would be for all of them or just one you choose?
Huh? One? How many do you have?
There are 5 of them that you asked us to design.
Yes,
We have 5.
So we're talking about one. Remember now that each person is going to be doing their own thing based on what they have chosen. But a combination.
Wait, based on what they have chosen. Wait, what do you mean, sir, based on what they have chosen? On the page, it says we must answer all questions.
Yeah, that's what I was wondering as well.
Hold on. Let me make sure that the communication doesn't get lost. Based on what you have chosen, mean what type of path, the communication path that you will be chosen for the different sections of the link that you're creating. Remember, I just gave you scenarios. So I could be going from Stony Hill using a microwave. I set up a microwave link between Stony Hill and Digicel. So I set up what's called a backhaul link between Stony Hill and I have direct line of sight, so I can set that up to Digicel and is it Beechwood Avenue? Their location. As long as that I will have gotten approval from frequencies, the frequency spectrum regulator, then I can set that up. Because if I don't get authorization, I can just put up a link just like that, you know. So I would have to get it authorized, eh? Then I can set that link. Or I could go, so that's one way of creating that communication straight into a digital or into a Lime office or location. Or I could use twisted pair cable and get my signal into the office, or I could use coaxial cable and get my signal to the office, or I could use fiber optics. So what I'm saying is that there are different types of communication path that you can use based on what you see fitting for each part of your communication link. So it's not to say that I'm saying that you're going to be selecting one. You're selecting, you're doing all. Because your design is your design. Do you understand me? It is your design, so you're gonna use your own specific way. So I'm not expecting on everybody to say, okay, I'm using this particular method. It could be a case when you check it out from a cost perspective. Digicel, Lime, or the existing service provider decide that they're gonna provide you with a link, but when you check it out from a budgetary perspective now, from an economic cost perspective, because it's a leased line, hey, you might find that it is costing you a lot more than if you had seek to provide a link to existing satellite service communication provider directly. It might cost you less, even though you might have to purchase your little own satellite network to uplink the signal to the service provider satellite in space. It is your design. What I want to see is the research that you put into design. That's what I want to see. And the logics of that proprietary work to see whether or not it actually makes any sense. Or is it something that you just created off the top of your head? And that's why I say it's a design, it's your design, because there are many different ways you can use for different parts of the communication link to get a signal from point A to point B. But there are two things that I suggested that you need to take into consideration, because that will guide you a lot. One is your actual budget from a cost perspective, and two, your link budget in terms of from the power budget. So what you know, I might be transmitting this thing, but I might need an amplifier that transmits at this level, as compared to a small amplifier that transmits at that level. And then I might have to put in 2 or 3 amplifiers as compared to the one that I might need. But the one that I need, from an economical perspective, might be too expensive. So it's best for me to put in 3 smaller size ones. Things I do, some logical thinking and reasoning, Communication theory.
So, sir, approximately when will you be able to upload the information?
I'm looking for it now. to upload. These are things that I have already. So I'm just going to go grab my resource and search for something. I have to be careful in terms of what I share, that I don't share everything, but just share some things that will guide you. Hmm. Yep, that's it. While I look, any other questions? Oh, okay. Oh, I know. Any other question regarding any other aspect of the course?
I guess the only thing we could possibly ask is what's going to happen pertaining to the labs.
You know,
I still haven't been able to do any labs.
that's a good question. That's a very good question. I'm not able to even get the lab tip myself. I don't know. The gentleman gave me another number. I tried to ask him if I could even share it to the students. I got nothing, no answer from him.
Actually, hold on.
Microwave.
She was in the WhatsApp group, and there was a time when we were gonna schedule a time for us to do the labs, but then once again the COVID-19 problem, so we couldn't do it. So I'm gonna have to ask who was in contact with him to ask when we can reschedule. Of course, it would have to be. It cannot be any time before. It cannot be a time this week because there's still restrictions. As far as I know, based on what people have been telling me, next week things are back to normal, and I think can happen. But we have to make some sort of plans. If we cannot go to the actual level, and we would have to see how we can compensate with doing a simulation, since that is the only way
I think he was.
I can think of right now that doesn't put people in harm's way and would not be affected by the COVID.
I think he was.
You're gonna say something, sir?
I think he was not object. As I said, there was some plans afoot to have remote sessions. I think that's where we probably need to go back to. Based on the challenges that we're having right now. That's probably the best bet right now. All right. Any other question? Because I want to move on to let's just finish this little other part while I'm looking for my updates and editing my update to send.
You're 33. Use your skills and confidence.
You definitely be missed here. Thanks, Fred.
Appreciate you stepping in on this.
I'm Chief Key SWAT membership. I personally requested you.
All right, if not, let's have a look at
What a great group it is here.
what's on my
You know.
what's been pre-shared right now. All right, so what I want to start look at, I think we mentioned it last time, was these two parameters that I use as a figure of merit to measure noise and signal strength in a communication system. We started last time by mentioning that you have what is called noise factor, denoted by a capital F, and we have what is called noise figure. So the factor comes before the figure. The factor, noise factor, is the ratio of the signal to noise power at the input of a system over the signal to noise ratio, the output of the same system. So that's noise factor. Noise figure is just converting noise factor to dB. So noise figure is just finding what is the power, the dB power ratio or power rating of the noise factor. Am I clear?
Yes, sir.
Okay. Now, a typical example, or even before I go there, no, one of the things that usually happens is at the input of a system, we know we can calculate the noise power given KTB, if you remember from last time, KTB, right? And you would know what's the power of a signal that is being inputted to that system. If it was in watt, we can convert it to dB. The noise is calculated in watt from KTB. We can convert that I'm teaching now. I'll call it back shortly. Yeah, sorry about that. So you can find the ratio of the signal to noise at the input of a system quite easily. But as the signal traverses the communication system, one of the things that we know for sure is that internal noise will be generated. And it makes the system signal to noise performance degraded because you're adding noise to the system as its signal traverses input to output. Hence, unless it's an ideal system, the signal to noise poor ratio at the input compared to the output will be different. And by extension, how much so different are they going to be is a measure of how much noise, internal noise, the communication system is adding as the signal passes from input to output. Now, one of the things that we also need to be cognizant of is the noise power is going to be amplified by the amplification factor of the communication system. So if we put amplifiers in the communication system trying to amplify the signal, that same amplification factor is going to amplify the noise power by the same margin, by the same factor. Hence, we have to be cognizant of that in order for us to understand the performance, overall performance of the system as it relates to signal to noise ratio. So here it is on screen that we're seeing a typical example of what is happening. So the equation that we're looking at, and I just highlight it here. This equation, it says is mathematically the signal to noise ratio at the output of a non-ideal amplifier is expressed mathematically as what's on screen, what has been highlighted. So it's a signal to noise ratio. So as I mentioned before, the signal is going to be the gain of the system, the power gain of the system, times the input. Because remember, output is input times gain. So it's a gain of the amplifier times the input signal. However, the noise at the output is going to be the same gain of the system, yeah, times the input noise plus any gain that the system would have developed internally. So the signal to noise ratio at the output of a communication of any system, in this case, would be, because the gain is common, you could just cancel the gain, the APs, and then you have signal to noise at the input over noise plus the noise over the gain. Everybody understand that equation? Everybody say we got that equation? Clear?
Somewhat, sir, somewhat.
Somewhat? Tell me what is not clear.
Basically, divide each term in the equation by AP. so that you can just have SI at the top.
This is random.
Or you could say you factor out AP, but it would be more accurate to say you divide each term by AP.
Okay, I'm seeing it better now. Thank you.
What's pipes and jobs? What's pipes? It's the band that plays the funeral. Oh, right. It's just the tip of the iceberg. Okay, we're talking parades,
All right.
baptisms, weddings,
Bear that in mind.
the Chicago land. You see, entering the brotherhood is like being appointed to the Supreme Court. It's a lifelong year.
Remember that the aim now is to find what?
When someone
The signal to noise ratio of the input over the signal to noise ratio of the output. And that is measuring what again? What's that measuring?
The noise factor.
Noise factor. Good. So here's a picture. And in a sense, here's a picture of what's happening. So if we had the first diagram, signal to noise ratio of the input. Remember this noise is determined by KTB, right? The signal is the signal strength that you're applying. The strength of the signal in dB or in watts. So it's the signal to noise ratio of the input of the system. This signal is going to go through the amplifier that has a power gain AP. If this is a noiseless system, which we know that is not even possible, then what will happen is that you'll have no noise added, and therefore at the output you have the signal output power over the noise output power, which is basically the gain times the input signal and the gain times the output signal, the input noise. And of course, the gains are the same, so the gain will cancel. So it means that if this is an ideal system, then the signal to noise ratio of the input will be the signal to noise ratio of the output. And by extension, the noise figure would be equal to
Wait, you were saying what, sir? What was the question you had asked?
for a system that is an ideal, meaning that there is no noise that is added internally to the signal when the signal traverses then the noise factor is going to be 1 because it will be signal to noise at the input over the signal to noise at the output, and that ratio would be 1 because there's no noise that is added. However, for a non-ideal system, which is more of what happens in the real world, again, at the input of that system, you're going to have a signal to noise ratio. But the system, which is going to tend to amplify, I have an amplifier, it's going to tend to amplify both the signal and noise. But the system is also going to add noise because we know that internal noise is generated, especially due to thermal noise. Right? And therefore, the noise figure is going to be the ratio of the input, which is SI, NI, yeah, over the signal to noise ratio of the output, which is given by the same thing that we had determined before. So just giving you two conditions. So here is an example, ladies and gentlemen, for a non-ideal amplifier and the following parameters. You must determine A, the input signal to noise ratio in dBs, the output signal to noise ratio, and by extension, the noise factor and the noise figure. Given that the input signal, input signal power is 2 times 10 to the 10 watt. The input noise power nicely is given us 2 times 10 to the minus 18 watt input noise power, right? Based on KTB, as you guys would have known. You're given the gain of the system as 1,000,000, and internal noise, ND, is given as 6 times 10 to the minus 12 watts. So based on that, not a problem calculating the first part, which is the signal to noise ratio of the input. Am I clear? Is that clear? Just simply 2 times 10 to the minus 10 over 2 times 10 to the minus 18, which gives you 100 million. That clear?
Yes, sir.
Yes, sir.
But you're supposed to calculate it in dB. So to calculate, to go from watts, ratio in watts to dB, it'll be on its power. If it was voltage, it would be 20 log, but it's in power, so it's 10 log. The 100 million, which equals 80 dB. The second part is for you to calculate the signal to noise ratio, the output, again in dB. Now, we know from the formula that we just created, I just saw that because the system is non-ideal, the output signal to noise ratio is going to be this formula. Remember, the signal over the noise power plus the internal noise divided by the gain of the amplifier. So that's the formula we're going to be using. So what's SI? SI was given as 2 times 10 to the minus 10, right?
Yes, sir.
What is NI based on this formula? NI is what?
So isn't
2 times 10 to the minus 18, right?
minus 18? Yes, sir.
Good. ND was given the expression as 6 times 10 to the minus 12, and the gain is a million. So therefore, it's going to be 6 times 10 to the minus 12 divided by a million. So that's what we're doing here. And that gives you 25 million as a power ratio. But that would have been converted to decibel by taking 10 log 25 million, which gives you 74 dBs. As you can see, ladies and gentlemen, there's a drop in this case of 6 dBs in the signal to noise power ratio from input to output. And that is all because of the added internal noise. Are you clear?
Yes, sir.
So you realize that we would have calculated the noise figure and the noise factor and the noise figure, because we converted the noise figure to decibel, the noise factor into decibel, and that gives us the noise figure.
It's actually, who's going to be here?
All right. Any questions?
Sir,
Yes.
so if you increase the gain, the internal noise matters less.
If you increase what?
The amplifier gain,
Mm-hmm.
the internal noise would matter less.
No.
What is ND over AP? So when you increase AP, it will get smaller, the entire fraction.
Remember AP, yeah, but remember now that
Is AP and ND correlated?
indirectly, yes.
Okay.
All right. Sometimes ladies and gentlemen, as you know, we have to cascade a system in order to get higher gain. Which means that we're taking it output from one system to become the input to another. So we said that we cascaded the system. Here on screen, figure 110 is showing 3 amplifiers that are cascaded. And sometimes we do need to do that because we need to get the appropriate amplification factor that will overcome the possibility of the noise of that is affecting the communication system. So if that's the case, it means that our noise figure is going to be affected, because the noise figure, the noise factor is the ratio of the signal to noise at the input as compared to the signal to noise at the output of the system. But reality is that you're going through 3 systems before you get the overall output. of the cascaded system are shown in figure 10.1, or 110, sorry. So you realize in figure 110, you're applying the input signal to noise ratio. Well, applying input signal input noise, you can measure the signal to noise ratio right then and there. And then that signal is inputted. And that's going to be again amplified and outputted as the input cascade to amplifier number 3, and so on and so forth. So it means now that we're gonna have to find a way to find the overall noise figure of the system. So it is done, ladies and gentlemen, is through the first formula. It is used to calculate the total noise factor of several cascaded amplifiers. And mathematically, equation 127 shows you how that is calculated. So the noise factor F in this case equals to F plus the noise factor of the second amplifier minus 1 over the gain of the first amplifier. And that's going to be added to the gain of the third amplifier minus 1 over the gain of the first amplifier and the gain of the second amplifier. And it continues as the number of cascading network has increased. As it increased, the formula is going to be the same as F plus 2 minus 1 over A plus 3 minus 1 plus 4 minus 1 over, instead of A now, it's going to be AAA. And that is what is done in our example as seen on screen. So just bear in mind this formula. Any questions so far? All right. Questions? Sample. .117. I leave it on screen. Person read through it. Look at how the answer is found and tell me if you understand what is being done. It's really plug in the formula, plug in values in the formula based on what's given. But it's also important for you to get a little bit of interaction with the formula before it comes a time when you have a formula but you don't know what to put in it. There are no questions removed. Remember, you are given noise figure and the power gain to find these. But understand? No questions? All right. The last thing that I want to look at on the noise is the equivalent noise temperature. Equivalent noise temperature. So remember, KTB is used to determine the noise power of a communication system. So from that formula, we can determine what T is. All right, one. Look at the reading and observe this. 1 quick second, ladies and gentlemen. All right. So, is it because noise produced from thermal agitation is directly proportional to the temperature? Thermal noise can be expressed in degrees as well as watts or dBm. And if we arrange the equation that noise power equals to kTb to find T, then T could have been expressed as equation 129. Now, as you can see in this cascaded diagram, we have two amplifiers. We have an input noise and input signal. Out of that first amplifier, we would have an output noise and an output signal considered to be S1 and S2. And obviously, the signal to noise ratio at the output of amplifier 1 will be different from the signal to noise ratio at the input of amplifier 1 because the system has a internal noise that has internal noise that will be added. But as you can see, ladies and gentlemen, the output signal to noise ratio of amplifier 1 becomes the input signal to noise ratio of amplifier 2, which ends its input and output. Amplifier 2 input and output signal to noise ratio would be different. Okay, now here's a pictorial representation of what is really happening, apart from what we just calculated or calculated previously. I said that this was a signal to noise ratio. So this input signal has a minus 10 dB, a minus 60 dBm. And the noise is minus 90 as well. Now, this is what I was talking about last time around with we were looking at the height for Chad and Mane. The heights are given in feet based on a similar reference point. But the difference between the heights are just measured in feet. It's the same thing here. Reference points are the same, that's why it's in dBm. But the difference in the signal level is 30. So the signal to noise ratio between the two signals in dB would be 30 dB and not 30 dBm. Because there's no need to measure with reference the difference, because we already state that two signals were at the same reference point by referring them to 1 milliwatt, right? Based on the gain of amplifier number 1, the gain is 10 dBs. So if we should add 10 dBs to both the signal and the noise, it means that adding 10 dB to a minus 60 dBm would take it to minus 50 dBm. That's for the signal, on the signal part. How about the noise? The noise now would be different because you're going to add 10, which would make it minus 80, but that is going to be affected by ND, which is the noise of the internal noise of the system, right? Which is what ND is going to come in right here. And likewise, ND2 is going to be added here to make the signal different. Are you following me so far? So that's what I'm saying. This is moving from 90 to 80. But when you add whatever value ND is, it's going to add to it to make it even higher.
I was hoping since Truck's still out of action, maybe let me work out. Sure, go ahead. Thanks, Casey.
Okay. All right. So Stuart, you can type. It's recording, damn. Okay. So, there's a typical increase based on what we know with our NDs that makes our signal to noise ratio between input and output different. However, we can actually measure the thermal effect of the system to the equivalent noise temperature, TE, where the equivalent noise temperature is a hypothetical value that cannot be directly measured. So you cannot measure what the equivalent noise temperature is. This is a convenient parameters often used rather than a noise figure in low noise, such as UHF and VHF systems. The thermal low noise but high frequency. The equivalent noise temperature can be measured as a noise factor component. So, long and short is, how do we use the noise, equivalent noise temperature of an amplifier? The equivalent noise temperature of an amplifier mathematically can be expressed as equation 130. Okay? And conversely, the noise factor can be represented. So from here, we can represent the noise factor F as noise equation 131. Here's an example. Noise figure so if we're given noise figure, we can actually use equivalent noise temperature to do our calculation without actually have to worry ourselves too much about finding all parameters that are given challenge, are unknown. So here, if you're given the noise figure or not the noise figure, sorry, the noise factor, then we could actually go ahead and calculate important factors such as your equivalent temperature or vice versa. So here's an example. Let's say you must determine a noise figure for an equivalent noise temperature of 75 K.
Hey, you guys hear that? Everybody fire out. We'll check it out.
You must also determine the equivalent noise temperature for a noise figure of 6 dB. And here's the solution. We substitute equation 131, and we found an answer that will give us the value for F. So substituting equation 131 into equation, of course, for Y, then it could give you the factor, as we mentioned before, F equals to 1 over 2 T e to the, well, 2. F equals to 1 plus T equivalent over T1, which is 1 plus. You were given a temperature as 75. And you're given the thermal temperature as the room temperature is 290 degrees. And we calculate to get the noise figure to be 1.258. And we can find the noise figure of that by just taking 10 log of the noise to get it in terms of the noise figure. The rest is self-explained. These are some questions that you could pose and ask yourself as a guide for understanding, okay? Any questions? Not, that is where we're going to leave it, especially for noise. No questions?
No, sir.
All right. Well, that is it for noise, as we're going to leave it for tonight. I'm going to do a little bit more search. And before the night out, I'm going to post what was requested by Mr. Stewart as a guide for you guys in terms of the design.
Sir,
Yes, Sir Williams.
what's the percentage for the final assessment? What percentage of the grade is it?
It's 40% of final grade.
Okay.
All right, well, let's leave it there. And we will. Oh, yes, I will send you individually. I finished marking them, so Stuart, I'll send them via email to each of you, okay? That's the grade for the test. All right. Guys, be safe. Continue to make sure you take care of you and your family. Do all that is required. I know it's a long weekend that's coming up. gives you some time to catch up on some of the stuff them that you are lagging behind. Use it well, okay? And don't get flustered by like others who want to go on the road and become COVID battle worn and want to go out. So have a good night, take care, and we'll talk as usual. I posted things as requested, and I look out for any email and provide feedback as per question asked. Have a good night to everyone.
Okay, very good.